Good afternoon. It's 3 o'clock here in Denmark now, in the afternoon. And I'm going to start this webinar now on experimental modal analysis. My name is Per Andersen, and I represent Structural Vibration Solutions. So this webinar here, this is concerning experimental modal analysis. I have a little outline here that consists of three bullets. First of all, I'd like to give an introduction to ARTeMIS Modal and to modal analysis, of course, and also the required license plugins that are needed in order to be able to do experimental modal analysis with ARTeMIS. And then after that, I would like to continue explaining the two ways that you can actually get information in that you can use to perform this experimental modal analysis. We are talking about frequency response functions that are required for this, and we will try to see how this can be accomplished. And then finally I will show the different modal analysis methods we have for experimental modal analysis, and I'll try to mix it with some test with a small test structure I have here on my table here next to me. So this is the idea. If you have any questions, feel free to write them in the chat or email us at this mail address here. Then we will try to respond after this webinar here as good as we can. So let's try and see what we can get here. We will start a little light with an introduction to modal analysis. And what we have here is a very simple structure. It's a kind of a beam or column or something that is vibrating here. So you could imagine this is in the physical domain here, that something has caused this to vibrate. And modal analysis is simply, you could say, a mathematical way of getting the modes of vibration that, you could say, give us this sophisticated vibration here. In some very simple ways. We get a mode shape, and we get a natural frequency and a damping ratio. In case of experimental modal analysis, we also get something we call the scaling factor. But these are the modal parameters. There is a set of mode parameters that describe one mode, and a structure can have many modes, you say, vibrating at the same time, depending on the way it has been excited and how it actually is designed. So this is modal analysis. That's a very, you would say, mathematical way to tear the vibration apart that can be measured and get these mode parameters extracted. And when we do that, we call this modal analysis. So there are different ways we can do it. We can do operational modal analysis that is also available in our software. And we can do this experimental modal analysis that I'm going to talk about today. There's also something called operating deflection shapes. This is another type of analysis of what's going on with the structure, but that's operating deflection shapes analysis is, you could say, doing an analysis on the physical behavior. So you're seeing the physical behavior in frequency and time domain when you do this kind of analysis. We are on the other side of the equation here. This is over here at the modal analysis part. We are doing things today. So we are talking about testing of a system, extracting the mode parameters of it. There are two fundamental things that has to be, you would say, fulfilled when it comes to making a good modal analysis. The structural system that we are going to test, it has to be linear and it has to be time invariant. Linearity means that it doesn't really matter how much you excite it. The parameters should not really change the size or the values of them depending on this vibration level here. If that's the case, then you basically have a nonlinear structure, and that's a little bit outside the scope of traditional modal analysis. So linearity is one of the things that we have to assume. The other thing is that we have to assume that the structure itself here is actually time invariant during the test we are doing. we cannot have that it's changing its parameters over time during the test that we are doing, because then we will get some kind of average values out in the end. So these are the two things that we normally assume for any kind of modal analysis that we are doing. Besides that, when it comes to experimental modal analysis, it's very important that we can measure the excitation that we are exciting the structure with. And of course also be able to measure the response that the structure is giving us when we are exciting it. So we have to be able to measure the force from the input and the, for example, acceleration or other types of response coming from the structure. This is what is required in order to make experimental modal analysis. So ARTeMIS Modal itself, you could say, is a tool that has originally been designed for operational modal analysis. But we have now, for some years now, had this opportunity that you can actually also do experimental modal analysis with the software. You need to have a few licenses added to your normal ARTeMIS license in order to be able to do it. There are two licenses, in fact, that are needed, especially the one we call EMA license, that is the one that opens up for the analysis tools we have for experimental modal analysis. This one here is required in order to do the estimation, for example, that you can see here, and to be able to process data that you upload, and if you want to create frequency response functions with the software. The other one, the DAC, this is the data acquisition plugin. This one is required if you are going to use the software here together with some hardware to perform impact testing. So if you want to do that with ARTeMIS, then you need to actually have a plugin, a license that opens up for, you would say, the data acquisition module we have in the software. So with these two together, you can do impact testing with the software. With EMA alone, you can upload, for example, your frequency response functions from files and do modal testing or modal analysis inside the software. We can try to start with the last one here. This is if you only have the EMA license available, then it can be that you have made your analysis with some other tool, some other hardware and software solution, and now you have a set of files that you would like to upload and then use the analysis tools inside ARTeMIS to work with. And we have here, this is a test of a car body. I think I have some files here. What is needed is when you want to do it without, you would say, or just with the files coming from another system, you need to have a file that consists of, you could say, the geometry. This file here is in universal file format. There are some different data sets here that describes, you could say, the geometry. And I'm not going to explain it here, but you need those in a file that you can then access. And then as you are moving around, let's say with shakers or with impact hammers, you are generating different frequency response functions. They are normally also stored in a particular data set inside the universal file format. And in this case here, there are 4 files. They have some starting information here, but what is important here is that there are these data sets number 58 here, because these are the ones that store this FRF. So one data set here is one frequency response function. That means one impact position and one response position recorded. So there can be many of these data sets here. They can be collected in one file or in many files. It doesn't really matter. But the way you get this into ARTeMIS to start the analysis, of course, you have to start ARTeMIS, and we can do that here now. Then you can go to new, make a new project here. Here there are a list of different options here, and when you have the Experimental Modal Analysis plugin available, you will see this part down here. And here there is a UFF entry here, if I click this one here, then I get this little dialog here. This one here allows me to select a file for the geometry, or where the geometry is stored in, and one or more files that storing the FRF information. We can try to click on this button here, and now we can select this one here that had the geometry information. And now we can click this little plus sign here. This one here will allow us to then find the files. I need to switch to UNV in this case here. That is also a known extension for universal file formats. I can then multi-select these 4 files here, because these are the ones that consist of the FRFs, and then I can click open and finish like this. And now all these FRFs and everything is now loaded into the workspace in ARTeMIS, and we can now see up here, we can see the model of the car here with all the positions where we have responses and also the impacts. These are the ones that has this little hammer here on the top here. And down here we have the mode indicator function that shows us, you say, the SVD, the singular value decomposition of the frequency response matrices that has been loaded. And then, of course, you can then continue now doing the analysis. But this is the way you can get, you could say, started with a project without having actually to do the impact testing inside ARTeMIS. You can actually also load, you could say, time series data. You can have force time series, and you can have response time series in files. You can then load it, and you can actually process it inside ARTeMIS also to obtain these frequency response functions. We have some different estimators for doing that also available. But normally, otherwise, it will be that you get them from universal file format through these frequency response functions that has been saved. So this is just a small introduction to how you can get started with a project that consists of files, you could say. Then we can continue a little bit, because we have this other option also that allows you to actually do everything inside ARTeMIS, provided you have some hardware that we support and that you have this DAC, the Data Acquisition License plugin. So if you have that one, this DAC license, along with the EMA license, and if you have some hardware that we support, then you can actually do impact testing using ARTeMIS. We have 3 different ways you can do it in ARTeMIS, and they are located down here. The first one is that you fix one or more outputs. That means you can put some accelerometers in different locations that can serve as your references. And now you can then move around with a hammer and then excite all the places where you like to know the mode shape. This is, you say, the default way of doing it in many cases. There is another one you can do also, that is that you can roll around with your output, and then you can, you could say, excite in a fixed position. That can also be done with the impact test, so you just excite the same place, and then you are moving around with your accelerometers from one location to another one, and then you're using the locations where you are putting your accelerometer in order to find or to get the mode shapes out. This is also the one you will use if you do shaker testing, for example. You will fix your shaker somewhere, and then you will probably move around with your accelerometers if you don't have enough to put in all the locations where you like to know the mode shape. And then we have the last one here. This is the one I'm trying to use today. It's not so often we use it, but here you can actually roll around with your output, your accelerometers, for example, and you can also use multiple locations for your input. So because everything seems to be allowed here, we call this the Wild West option in our software, because it's a little bit on your own. You're on your own here now. There is not so much control over what you're doing, but I'll show you how you can see that you are doing things right, of course. But this is the one I'm going to try to use here now. We have this little plate here This is very simple, and this is the one I often use in my webinars here. Today I'm going to place 8 accelerometers first in these 8 locations up here. And then after a while, I will be placing them down here instead. Every time I have, you could say, a setup of my accelerometers here, I will then impact 3 times in this location here and 3 times down here in this location here. Then I will move these and then do exactly the same again. So I'm moving with, you could say, both the accelerometers, but I'm also moving with the input. The reason why we made this one here is that we have some customers that has problems, you could say, accessing the points where they like to know the mode shape. So they have a kind of a machinery that is very difficult to get in with the hammer and then excite all these points where the mode shape should be known. It's easier just to excite a few places. This is a cylindrical structure that we designed it for. So you have to impact one direction and perpendicular to that later on. And then you can move around with a block of sensors, which is easier in this case here. So for accessibility reasons, this was made in this way here. So you can see here, this is what we have. We have National Instruments hardware. This is a 12-channel unit I'm having here. I have 8 accelerometers. And I also have this impact hammer that you see here. And now I'll be using this kind of rowing technique here that I have tried to explain here. Let me just, before I continue, I can try to see if I can get things pointing down here on my table here. Hopefully you can see now my data acquisition system here. And here you can see the hammer, and here of course also the plates and the 8 positions we have here for now. The first, you could say, initial setup of the sensors. Let me go back now to ARTeMIS here. So now I'll start a new project. I'll just close this one here. And then we will start another one up now. Now it has to be a blank project because we are going to start from scratch in this case here. And now we are having a blank project. As you can see, not much is happening right now in ARTeMIS. We are inside the task here that is called Manage Measurements. This is the typical place if you have been loading some data to begin with that you would like to go. But in our case here, let's go and define a geometry, this plate. We do that by going to this task here called Prepare Geometry. And here we have this, this drawing grid here. And what I can do is I can make a very simple drawing of a plate just by going here to this list of objects I have here. I have this filled rectangle here I can choose. If I click this one here, then I get this kind of pen that marks where I can start my drawing. I put it here in the origin of the coordinate system. Then I keep my left button down on the mouse, and then I drag it to the other side here and release it like this. So now I have my plate here. I can now try to do a little bit of subdivision here because we need to have more than the 4 corner points we have here. We need to have points for all the different sensors and the impact position also that we have. So let's just start by subdividing X and Y here of this plate here. So now you can see here now we get much more nodes here corresponding to the number of nodes that we need actually for the accelerometers in this case here. Then we need 2 locations also for the impact, and we can add points by clicking this little button up here. And now I can then go and I can find a spot that matches more or less what I have on my geometry here on the steel plate. I put these 2 points here in these locations here. So this is what we need, you could say, when it comes to geometry. We can now go to the next task where we can design our test, how we would like to impact and move around with the sensors. If we go to this is the assign DOF information task. This is the third of these tasks here in the first part of ARTeMIS project here. If I go here now, then I can start clicking here on the new measurement project. Here I get the list of different EMA testing types, as you can see here. I have here, if I expand this list here, I have you could say the default one I normally will use, but I have here the one where I can roll around with output and input like this. So I can select this one here in this case here. And then you could say the logic of the data organizer here changes based on the choice that I have made of EMA testing type here. When you switch it here to rowing output, rowing input, you will not be able to see any color change of reference and free moving sensors. All this is disabled. This is why we call it this Wild West option here. But what we can do is we can go here and we can now insert one test setup, and then we need to insert 9 channels because we have the hammer and then we have 8 accelerometers. And then my hammer is sitting over here in channel number 1. That's the black PNC we can see here. So the first channel here, this is my first, or this is the impact hammer. This hammer here is first of all not an output, it's an input. So we have to select it here to be input. And we also have to direct it in the right direction, because right now we have to be on the bottom of the plate and then impacting it in the plus Z direction, which is not very convenient. So I will change it here to minus Z, which means that I can make the impact going down into the table, you could say, in this case here. Now the rest is just to put, you could say, the accelerometers in the right location. Again, these are pointing in the plus Z in vertical direction, like this. So we need to direct these to plus Z like this. And you can see I'm simply dragging them out here now in the order that I placed them in. So let's see if we can get all the way through here like this. This is the first setup. So that means I will be impacting in this location here. Let's see, where is the mouse? This one here. And I'll do that 3 times. And then I'm done with this setup here. Then I'll do another setup where I keep the accelerometers in this location here, but I move the hammer to the other location over here. To do that, I will replicate this setup here. This is the easiest way to, you could say, copy as much as the information and keep things like directions and so on. So I will simply click this replicate here. And then I will say that let's keep all the outputs here because they will be sitting in the same place. So we will keep those. So now you can see I made a copy of it where these outputs, they are sitting in the same location. The input is red, it's disconnected. I have to drag it out now to the other location over here and put it there. In this way here, I now get, you would say, the second setup. You may see something that is gray here. This is a ghost mode. This is just to indicate that something has already been put here. We can actually remove these if we don't, if you don't like to see them. Let's see if I can get my little geometry under control here. I think it was like this. Yes. If I unclick this ghost arrows here, the gray arrows, they will disappear. So we can see now that now we have the actual setup that we were using here. So this is the second one. Now I will go up here again and I will replicate this one here one more time. And now I will just keep the reference and nothing else. And I will click replicate. And now I have a third one down here. The only thing I have now is actually the input. So I will have to put them over here now. This is the when I move with the sensors now to the new locations, but I keep the input in the first location. So let's see here, I will just get this over here, like this, and then one more, like this. So this is my third setup, and I'll be impacting 3 times here in this first location here. And then finally I have to replicate this one here one more time. And now I will then keep all these outputs here, like this. And where do we have it? I have to go down here. And then I'll drag the impact position here. So this is my fourth setup. So now I have them all. Just to be absolutely sure that I didn't mess up anything, I will always just click on it and see, okay, this looks okay. This one is okay too. This one seems okay. And then we have this one. These are the 4 setups that we are going to use. Now let's try to perhaps start by saving this stuff here. Just to be sure we have something. And then I go now to data acquisition. So because now I like to do the actual impact testing. So I go here now and I select, you say, the hardware that I have connected. In this case here is the National Instrument hardware we have. And it will now detect what is actually assigned to the different channels here of sensors and so on. It can find all the ones that are TETS sensors. The one that doesn't have this information, you could say, stored inside the sensor, will have to be manually added, you could say. And in this case, the first one here, this is the PCB hammer. It does not have any TETS information, so I have to find it here in my list of supported hardware, and I have it here. So now I have all my channels configured, and we can start the actual impact testing module. What I have to do first is I have to inform, you could say, or link the channels I have in my 4 setups. I have to link them to the hardware that I connected. Normally you will of course put your sensors and so on in the same order as you have had defined it in your project, but it could be that you for some reason cannot do that. But if it is, you would say, the same order, so first channel at the hardware is the one we have defined as our input in this case here, and vice versa with all the different accelerometers. If that's the case, then you can just press this auto assign, which will automatically then link all the different channels together, channels we have defined in the project with the hardware channels. And we can see now that everything lights up in green here because they have all been linked together in the different setups. The next we have to do is we can start by, you could say, trying to see if we can get some displays that will show us something. We can put some of them here. So here we will see the first channel. This is the force. This is the one we will have up here. We will see something in time domain and something here in frequency domain. And the same for the first acceleration accelerometer. It will appear something here in time domain and something in frequency domain here, and so on all the way down. But before we can see anything, we need to configure the hammer and the data acquisition, and we do that inside this hammer setup here. So inside here, we have 2 things we basically have to do. The first is we have to define what level that we should trigger on when we do an impact with the hammer. But of course we also need to configure what we would sample with of sampling frequency. And I will start doing that. This plate I have been testing a lot of times, so I will go to 5120 Hertz because that gives me a very nice, say, range of modes. I also know that this plate is quite likely damped, so I would like to have 2048 samples available. We can check this in a while, why I'm choosing this. but let's just do it now, not to waste too much time on that. So what we need to do now is we have to start, you say, the data acquisition system, and then I have to take the hammer now, and I have then to try to impact different locations here and get some impacts recorded, so we can find out what is the level actually of newtons we have here from this impact here. And we can see these impacts here popping up here now in this diagram here. So I can stop here. And then it suggests some values, and we can just say yes to this if we want. They are a little bit high, I think, 16 newtons. What I can do is I can lower them a little bit by going here and then lowering this value a little bit down to around perhaps 10 or something, 11, around here. Then whenever we have a hit with the hammer that exceeds this threshold here, that we have this stipple line here, then we will start a recording. And then we will record the impact and the response that is coming from the accelerometers. The next thing we have to do is we have to configure windows. We can put some windows on the force, that means on the input measurement, and we can also put windows on our response measurements. They have to die out, you could say, the responses so that they become zero in the end of the free decay that you get. If that's not the case, then you have to apply a window to the response. We will start now configuring, you could say, a force window. There's really no need not to apply a force window when you have a hammer here. At least I cannot see why you should not do it. So what I'll do is I would like to show the raw time series and the window that I'm going to define. I can do that by selecting this option here. And then I like to actually select a force window here. The force window will actually keep the force of the impact, and then it will zero out everything a while after, so that we actually don't get a lot of noise recorded in the end that is going to be messing up our, you would say, spectrum estimation of the force. So let's try and see how it looks. I can try to start again, and then we can do an impact and see how it looks. Because I was hitting the table, I'll try again. All right, so here we see now the force being recorded here. We can see how the window is operating here. It's from this point here, it zeroes out everything here. We can also see over here, this is in frequency domain, how the force is a very flat spectrum like this. Down here we can see the time domain recording of one of the accelerometers. And we can see how it's nicely dying out to zero here, which means that we don't really need any kind of windowing for this response here. Over here you can actually then see spectral density of this particular channel here, and you can see then the different places we have resonance frequencies. So we say everything is good here, and then we will try to start our little exercise here. I will start, I have, as you can see here, set up for 3 impacts every time. So if I start now, the first location here, okay. Before we continue is we can actually open this FRF matrix here. This is a little convenient tool that allows us to see what part of the FRF we are actually working on. Let me just make it a little bit smaller here. So here you can actually see that we have just completed the green part here. So that's the first locations of the accelerometers and the first impact position. Now we are here where it's red, up here and then down here. So this section that we see over here, this is what we are going to impact now. So let's try and do that. Just see here. We see it gets yellow now because we are on its way. We're not complete. then the final one. Before I start impacting again, so I will start by moving these sensors here to the bottom here. Yes. All right. Good. And hopefully they are all sticking there. Like this. So now I have to impact, as you can see in the geometry up here in the first location here. The actual test. We can now go and we can check out the FRFs in the managed measurement task here, where we can then see how they are looking. We can inspect all the different ones we have here, individual impacts in this section here, where we can see it, and we can also look at things like if we want to change from looking at the spectrum, we can look at other things here like coherence or other things. All this can be viewed here in this task here. So this is actually, you could say, the test itself now, impact testing. We have FRFs available now. We are ready to actually go and do a modal testing. Let's go to the back to this little presentation here before we continue with this. Just to explain the two different methods we have available. We have a non-parametric method and we have a parametric method. The non-parametric method is one of the many we have in our software. We have several, as you can see here, for operational mode analysis, but for experimental mode analysis, we have the complex mode indicator function, peak picking method, that we call CMIF in our case. This one here relies on that you actually estimate frequency response functions. You then transform these, we say, to modal domain. And then based on this, you can then do peak picking and extract the modes in this case here. The way it works is if we start from the, you could say, operational mode analysis part, it's exactly the same way we do it both for OMA and EMA. So let me just start here from OMA. You can imagine that we have, in this case, a spectral density matrix, or if it's in EMA, it's what's called a frequency response function. This one here, we can then, theoretically, we can, you would say, transform it with this similarity transformation here, where we have another, you would say, spectrum inside here that is the modal coordinates in case of OMA. So this is theoretically what is happening when you have mode shapes outside on both sides here. You can then come from this modal coordinate spectrum here out to the physical spectral densities that you can measure using accelerometers, for example. So if we now inside the software try to, we would say, emulate this in some way, we can do that by performing a singular value decomposition to spectral densities or frequency response functions. If we apply this singular value decomposition to that, we get some left singular vectors. There are also some other vectors over here that in this case here are the same, but this is only for OMA. But we have left singular vectors here and we have singular values here. It turns out that in the vicinity around the peaks, these singular values, the first one here, is very, very good representation of the modal coordinate. And the left singular vector here, this is actually a good representation of the mode shape. So what we do is we will make a peak picking at the peaks of the modes, where they have the resonance frequencies. And then we will extract the first singular value. Corresponding to this one here, we will then find the singular vector here on the left. You could say the left singular vector. And this one here is a very nice estimate of the mode shape. And we can immediately animate it, and we can use it to estimate also damping and improve the frequency estimate and so on. But the first fundamental part is simply to extract this one here to get the mode shape. And this is what we do in the FDD method. What is really important to make note of is that we need to have, you could say, the rows here corresponding to the mode shape coordinates, because then it matches what we have up here in this similarity transformation. Here we will have the mode shapes out here. So it's important that the matrix that we are applying this SVD to has rows that corresponds to the mode shapes that we will get out. This causes a little bit of an issue, you could say, when we're using it for frequency response functions. In our case here, we will actually have, you could say, 16 rows, because we have 16 response positions, and we will only have 2 impact positions or 2 columns in this frequency response function or matrix. So we are good here. We have more. All our rows here are used for extracting the mode shape. But if you're doing an impact testing normally, where you have maybe 2 accelerometers sitting here on the plate, and then you are moving around with your hammer, then it's actually the input positions that you are going to use for mode shape extraction. And when that's the case, then you will have to work on the transpose of the FRF matrix. But don't worry, all this is done automatically inside ARTeMIS. We are just transposing this frequency response matrix before we do the SVD of it. But this is there are some tweaks that has to be done there in order to make it work. But the way it works is that you can simply do peak picking on this singular value decomposition, and we can try go back to the software just to quickly do this. I will simply go here to prepare data. This will then collect all the different frequency response functions, and it will calculate this CMIF or mode indicator function here. We can also here look at the FRFs and so on, but what is more important is if we go to estimation, we can actually now start doing peak picking. I simply click on this add new button here, and then if I click here, you can see immediately I will get the mode shape estimated here like this. So in this way here, I can click my way through, and I can get the different modes I have in this particular analysis here. So let's see. This is the first, you could say, type of estimator we have. Then we have another one also. It's a parametric method. It's in the same class as the SSI methods that we have for operational modal analysis, but the one we have here for experimental modal analysis is called rational fraction polynomial, RFP-Z we call it. But common for all these methods here is that they are relying on that we are estimating some parametric models that we estimate with increasing dimensions. So we estimate a range of different models. These models here, we will then find or extract the natural frequency, damping ratio, and mode shapes from, and we will then construct a so-called stabilization diagram where we show the frequencies of the different modes, and we can use that to see which of all these modes that has been estimated that looks to be physical modes. These are the ones that stabilize. They become perfectly vertical lines they are lying on. And then the software is designed to pick them out automatically, the ones that have stabilized, and then make an average of them so that we get, you would say, very nice estimates of global estimates of these modes. So these are the 3 steps one has to go through when you are working with the parametric models. The one we used was this RFP-Z, and it comes from that we have a rational polynomial. That is this kind of division of two polynomials here. So we have a numerator polynomial here, and we have a denominator polynomial down here. This polynomial down here, the roots of that one is in fact related to the natural frequencies and the damping ratios that we are looking for. So we have one here. This is a rational polynomial that describes a single, you could say, discrete frequency for a single frequency response. So this is not a lot. So the first we have to do is, of course, to extend this to work with, you could say, multiple frequencies. Because we are measuring from 0 and then up to a Nyquist frequency that is, in this case here, with our test we did here, 2,500 Hertz. So there is a lot of things going on in this range here. So we need to be able to work with multiple frequencies in this estimation we are doing. And the extension of what you saw before to multiple frequency lines, well, it of course extends also the formulation a little bit. But you can still see that here you have the polynomials in a vector form now of the denominator polynomial. And over here you have the coefficients of the numerator polynomial. Here we have FRF values of the different frequencies for a particular frequency response stacked together here. And here we have this set operator here that is just a kind of a, you would say, formalistic frequency. And then over here we have again something related to the FRFs. So the only thing unknown is this one here and this one here. Everything else can actually be either measured or defined, you could say, as a part of the analysis. And that means if we can put it into a matrix form, we can isolate everything that is unknown into this vector here with the two sets of polynomial coefficients here. The rest is known here. Now we have to extend it even more because we're working with a single FRF. That means a single position of our impact and a single position of our response. We need, of course, to have the full FRF matrix covered with our analysis here. So we need to be able to work with multiple FRFs at the same time. So going from, you could say, this formulation here for a single FRF at multiple frequencies, we now stack this actually for each of the FRFs. And then we get this terrible formulation here that is now even worse than before. But with a little bit of, you could say, manipulation of all this, we end up with this nice little relation here, where we have a matrix here that is completely known. We have an unknown A matrix here. This is the coefficients of the denominator polynomial. And then we have something known over here in this vector here. So if I now invert this one here and multiply over here, then I can actually now calculate the A coefficients by a linear regression. Once I have this A here, it turns out I can stuff it in down here, and then everything else is known up front. And then I can actually calculate then the coefficients of the different numerator polynomials that I have for each of my FRFs. So in this way here, I can, with a little, you could say, gymnastics of FRFs and other things and linear regression, I can actually extract all the parameters that are needed in order to both get the modes, but also ultimately get the mode shapes. The mode shapes, they are coming out from this relation here. We have the residues here. This is for a particular, you could say, FRF. We have it here in a particular pole. Once we have extracted the poles from that means the roots, you could say, of the A polynomial. These are the poles or eigenvalues. They can be put into this relation here, and now the only thing unknown is actually this residue here. And then all of this again can be formalized into this regression problem here with a lot of big matrices where the only thing unknown is these residue values or matrices, matrix coefficients over here. And once these has been estimated based on linear regression, then we can actually also extract the mode shapes. So there are some different steps, as you can see, that we have to go through. But again, let's keep that to the software. We will let this do it for us. And if I go to the software now, I can try to switch now to the RFP-Z. And then you will see now we are seeing, you would say, an empty stabilization diagram right now. What you see in here is just the mode indicator function that is lying there in the back, helping us to indicate where modes might be. Then what I have to do is basically I have to tell what maximum model order would I like to estimate. That means how many coefficients of my denominator polynomial, or how many eigenvalues do I want to estimate. And here it's by default set to 50. But that means if you have more than 50 eigenvalues that you need to estimate, you might have to increase this number here. But if you are okay with this number here, you just press this estimate models button up here, and then automatically you can see the stabilization diagram is created. Everything that is red here is good, because this is actually indicating stable modes. So all these modes here, they are indicated to belong to each other. I mean, it's the same mode extracted with different models that has been estimated. And then you can see perhaps over here, up here, there's a tiny a. This means that the software automatically has figured out that all of this belongs together. And then it's actually taking all of the frequencies here and averaging them together. It's doing the same with the damping ratio and the mode shape also. And in this way, we can then get all the values that you can see over here, where we have frequency, we have damping, we have also the mode shape in behind, and that enables us to calculate this complexity value here. That tells us something about how real this mode is. The closer you get to 0%, the better. So the first one here is quite complex, I would say. We can try to animate it and see what it looks like. It's a kind of a rigid body mode we have here. The next one here, you see, it has much less complexity here, and we can also see it's the first bending mode we have here of this, or torsional mode we have of this structure here. So this is the way that RFP-Z is working. It's actually creating, you could say, more or less by itself, most of it. You can then work in different ways with it, because you can, for example, use these small triangles up here. If you don't want to work with all the modes here, but there are a subset, let's say we want to only work with this part here. Maybe we want to exclude this one here, that is the first one here, like this. Now everything inside the white area here is the only thing that is actually being considered. We will regenerate, you could say, a new frequency axis in Z domain for this one here, and then work on this alone. And you can now see how it's only modes inside here that is being estimated. So in this way, you can then zoom in on the parts of the FRF that you need to find modes for, and then leave everything out. There's no need to estimate or spend computational effort to estimate modes that you don't need. So this is the way you can operate this RFP-Z. And otherwise, there are different kinds of ways you can set it up here, so that you can, for example, limit which mode you're looking for. If you know that you're only looking for very low damped modes, you can then put a maximum damping here, and then everything will be excluded that has too much damping, and so on. If we had also made accelerometer measurements in these points here, and this point here where we were impacting, and the other point down here, or at least one of them, we would have something we call a driving point measurement. And that would have enabled us, or enabled the software also, to actually calculate the scaling of the mode shapes. In this case here, they will not be scaled, you could say, or you will not find the scaling factor, because you are missing this driving point measurement. But this is of course something that you could add also if needed. So let's just go back here to our little presentation again. Just to give you some final remarks here, just to wrap up that ARTeMIS Modal is a very open software platform, because you can actually import from other software platforms data in and then use the analysis tools we have in the software alone. You don't need to use you make the measurements inside ARTeMIS. You can actually do it many other places and then just import your data and then do the actual analysis inside ARTeMIS. And we can use frequency response functions from other tools through the universal file format. This can be uploaded in this way. Or you can also, of course, use our own impact testing module in order to be able to get these FRFs determined. We support right now 4 different types of hardware vendors. There will probably be more in the future, but right now these are the ones. And here in the office we have most of it on our own, so that we can try it out on our own. Then when it comes to experimental modal analysis, we have right now 2 different methods available in the software. We have the CMIF and the RFP-Z. And I have tried to show you both of them here today. And depending on what you could say version of ARTeMIS you have, you then have different ways you can validate, you could say, your measurements or your results. Because if you have a basic version of ARTeMIS, there is a limit to what kind of validation tools we have. But if you have the standard version or the pro version, you have other kinds of validation where you can then compare the different modes with one another, or you can upload modes from other tools and then compare with those. This is available in the standard and the pro version. So there is a little bit of, you say, differences in what you have of validation features depending on what version of ARTeMIS that you're running. But in total, you say you need to have always at least the EMA plugin in order to do experimental modal analysis. And you also need to have the DAC license if you need to do impact testing with the software. So basically, that's what I have to say. I like to say thank you. And if you want to see more, you can go to our YouTube channel, where this webinar, along with previous ones, align and all the kinds of instruction videos are there too. We of course also have our website where there is both literature and software download for testing. And then I like to perhaps advertise for the next training course we have, that is both for, you say, experienced users, but also new users of ARTeMIS. And this will be here in Denmark in April next year. And then the next webinar I'm giving here will be also next year in start of March, where I'll be talking about the structural health monitoring plugins that we have for ARTeMIS Modal. Thank you very much.